Good morning. So, we continue with the end of yesterday. You remember yesterday I showed you, because we don't have time, I showed you that machine learning can be divided into 4 big families: supervised learning, unsupervised learning, reinforcement learning, and now it's self-supervised learning. I showed you for each one just a list of what kinds of methods correspond to which class and what type of problem is working. So, of course, as I said, we don't have time to go into the details of every single method. But what I can show you some general rules and some general knowledge that can be applied to all the methods. Okay, that's the idea, is to give you some way of addressing all the methods with things that are common. The particular details of method, this method or that method or another method, that, you know, we cannot go into all these details. But the question is also, I'll speak about how to choose methods. Already I gave you my 2 tables at the beginning, or supervised and unsupervised. Those are very important things. I told you these tables don't exist anywhere except here and in my book. So those are very valuable because they give you some guidance, initial guidance. You've got some data, and people say, well, I'm going to do machine learning, but then you realize, the data has certain characteristics, it has labels, it doesn't have labels, etc. And the machine learning is a huge jump of many things. At least you have some initial guidelines of what kind of method to choose. And I'll speak today about the importance of measuring the performance. In other words, it's a good to have a model, but we have to know, does the model do a good job? We have to measure its good or bad, its performance. When we do classical direct analysis, it's quite easy because we have convergence and we have orders of convergence, and you can say, you know, if I have a method that's h squared, that has quadratic error big O of x squared, in order to divide h by 2, then the error will decrease by a factor of 4. Okay, machine learning is not so easy because they are not convergence results. It doesn't exist convergence results, per se. Okay? So what we can do is we can adjust parameters in the model, make them more complex, make them more adaptive, and see. And we can also use different methods, different approaches. I showed you the table. Some methods have low complexity, others have high complexity. And as I said, we use the principle that we use the method of lowest complexity in order to attain a reasonable performance. But this becomes very important because we don't have convergence results, error estimates, what we call error estimates, like we have in traditional computational science. So that's a big problem. So one has to have some way of measuring the performance and then doing what we call validation. I'll speak about validation. Validation is very important for the simple reason that we're dealing with random data. Because it's data, it's random, it's real stuff. And the question is, because the data is random, if I take the data today and I take the data tomorrow, they won't be the same. Right? That's life. You know, as I said, if we genetically we're all the same, life, you know, doesn't exist. You just look at each other and see how different we are. Everything. There are variations in nature, and if you use in nature or science, there are going to be variations. So the question we have to ask ourselves, how do we validate? In other words, how do we ensure that this fantastic machine learning algorithm that we use on today's data or on a certain collection of data will also work to the same, or be at some kind of robustness for the data of tomorrow, which definitely will not be the same as the data of today. Forget it. So it's not 5x equals 10, it's not ax equals b, it's ax equals b plus zeta, and zeta is some kind of random variable. That's life. Life is very simple. People say, what's the meaning of life? It's simple. ax equals b plus beta, and beta is a random variable. Do you understand that? It's a very simple mathematical representation of the world. some relationship between an unknown variable, you can say y. You want to find x variable. So let's think about this. So let me show you an example. I call it too much of a good thing. So let's say that I have some kind of green function I don't know. Okay? I only have the blue points which are random data sampled from the green function. I did, in fact, the green function is a sinusoid. Okay. And so I want to approximate, I want to find the best approximation to this green, which I don't know. I only know the blue point. Okay. So my function, in fact, I have measurements yi, sine of 2 pi xi, x is y, plus, there's my epsilon. Epsilon's a noise, that's the world, that's reality, that's nature, that's something. Otherwise we're doing something. You can say, oh, I can take the average value and you get epsilon, that's average, as expected, so mean equal to 0. If epsilon is a mean 0, so that's the process of mean 0 random variable, then the mean of y, that's true, the average value is sine 2 pi x. What we learned all through school, from the first day of school until into university, we learned only the average value of this equation. But in fact, the average value is one possible solution to this equation. It's only one. If you want all the solutions, you have to take epsilon. So here's epsilon, the blue circles are my y. I did this. Okay, so you could write a code in 3 lines. So I said, okay, let me try a very simple model. I have to choose a model now because I want to find something that can approximate the unknown underlying. I want to discover how this thing works. How I discover how it works, then I can forecast it. I can continue and say what will happen if I have another x, which is out here, where the x is one of the points that has not been measured before. This way I can understand the system, analyze, modify the coefficients in the system and see what happens, because I have a model that finds this functional relationship. Because I only know the y, I don't know the x. Okay, so now these are my input output pairs, so I'm going to do supervised learning. But I'll do something very simple, I'll just do regression. So you can say, let me try a polynomial over 0. Polynomial over 0 is just a straight line. It's just a constant value. First, the 0th order polynomial is a straight line. So it gives me the red line, so that's not really a very good, okay? It's not a very good model for the science. So you say, okay, I'm going to go and do increased complexity model. Okay? So this is how we model. Okay? One level. Now I'm going to try first order polynomial. So we know first order polynomial is a straight line. So if I adjust, I use regression. Regression, I told you, is the most basic method of machine learning. It's called regression. Yeah, I can do linear regression. And I find a straight line. Okay, it's an interpolation. You see, it's catching some of the tendencies, but it's not catching, for example, the peak values and the extreme values. Not. So obviously, I'll say, okay, that's great. I understand. What's up? I'm going to go up. Try it out. Third order. Okay. You see the progression. Yeah, I want you to see what's happening. 0th order, first order, third order. This is starting to really interesting. You see the third order polynomial adjusted the best. It's an optimization problem. Linear regression is an optimization problem. It's starting to do a good job. So you say, now I understand. All I need to do is increase the order of the polynomial, and I'm going to get better and better approximations, right? It seems logical. So what happens? So you say, okay, now I'm going to go a bit crazy. I'm going to try 9th order polynomial. What happens with 9th order polynomial? You see, my red curve, my interpolation, my recursion, it fits exactly the data, exactly. So if I calculate the error, I only know the values of these data points. You see, I would see this guy, this red guy, which is completely crazy because it's a highly oscillating polynomial, very high order, has done an excellent job of capturing the values. In fact, if I measure the error, calculate the error. What's the error? I showed you that the error is the norm of y of 1 minus y hat is the approximation. Y is the measurement of the oscillation. We want to minimize it. Linear regression is just about minimization. So this is if I take 1 over n, then that's what's called mean square. Yeah, yes. Which is one of the most common ways of measuring the precision or the performance of any machine learning or any approximation method. Very simple. Just take, this is the norm. If I would write it out, the norm I would write it's a Euclidean norm. It's a fact. It's 1 over n sum I equals 1 to n of 1 I minus 1 hat. That's the mean square. That's how we use this is NS. What's happened? My terrible approximation has a mean square error which is almost equal to 0. So if you judge, this is why I'm warning you. I'm warning you because this is the case for linear regression. That neural networks and other machine learning methods become more and more complex. Complexity means you reduce what's called the bias in your method, but you're increasing the variance. In other words, the uncertainty now if I take a C, I want to know the value at this point, I'm going to get an approximation. My y hat, what my machine learning algorithm is giving me, is completely wrong. Okay? But I have the impression that I've done a great job because MST is close to 0. This is what happens. See, what happens is that the mean squared error, this is the mean squared error, is going down. At 9, when order equals 9, I'm almost at 0. Okay? And then you see there's another curve. What's this red curve? That's what's called the test curve. The test curve, this is what the blue curve is called the training curve, because I'm training my model. I'm trying. Training means I'm trying to. I'm training. This doesn't go too well. I'm going to improve. I'm going to learn that one. I'm going to learn the next one. And finally, I'm happy because I've got an MST that's very small. I think, great. I can publish now. Then what's going to happen? Somebody's going to come along with red data and test. In other words, I'm going to take data that was not used for the training. It's called unseen data or new data. That's the whole idea. Why we do machine learning? It's not so that we can reproduce the training data, because we trained the machine, we trained the algorithm. We solved the linear regression problem, the minimization problem. That's the linear regression. The min is LR, linear regression. LR is, like I told you, it's one of the basic. It's one of the first methods we use in machine learning. It's a machine learning method, linear regression. Sometimes it's called simple linear regression, sometimes it's called ordinary OLS, it's called ordinary least squares. It has many names, but it's always, for me, it's just linear regression. And we can solve this. Quite easy to solve. It's finding the blue of a quadratic function. Okay, so, great, we've solved the minimization problem. We have a very small error, and now we're going to give the machine here. We're going to give the result. Train the algorithm to somebody else who's going to use it. He's going to use it, or he or she's going to use it. They're going to have a point that's somewhere here, or a point here, or a point here. So what happens? They're going to test. So you see what's happening is that the test error, I measure the error by testing. What happens is it's going to decrease to a certain point, and then it's going to start shooting up. Shooting up here, that's because I've done what's called overfitting. That's the great. It's called overfitting. What happens, instead of fitting the observations or fitting the trend, the green line, I'm fitting Big, big danger. Why? Because we want to be good students, we want to be good scientists, so we say that we have to have a very small mean square error, and that means we do a good job. And the square error, very heavy. Oh, good job, good job. Good job. And then the problem is somebody's going to say, you're going to give it to the doctor, to the neurologist, to the seismologist, to the climate, to whatever. And they're going to use your method, and they're going to get terrible, terrible, terrible predictions. Why? Because you gave them an idea of a polynomial, but you say, I won a big prize, but it's zero. Close to zero error. You see the errors. And in fact, what's happening is the coefficients of the polynomial. If I look at the polynomial coefficients, you can see the coefficients going crazy. See the coefficients here are 10 to the 6, 10 to the 5 times to the 6. They're going crazy, whereas for the third order polynomial already I'm getting some quite large coefficients, and obviously these coefficients have what's called high variance. So it's what's called I'll show you the last time. Remember, it's a simple example, or it's a stupid example. Life is not like that, but life is like that in fact. We are often looking for relatively simple patterns in the data. That's a simple pattern. It's just my zero. It's just the science of it. That only have noisy data. I'm going to try and fit. This is underfitted. I'm not fitting it. And so I'm going to push the complexity slowly. This is more or less good. And you see, I can go too far very easily. That's what's called fitting the noise. I found a curve that corresponds exactly to the noise in the data and not to the tendency or not to the underlying variation. Okay? So this is a big danger. Why is it a danger? Because we have neural networks. The neural networks are the world champions of overfitting. Sometimes, I don't say that sometimes one needs, if my green curve was very oscillatory, which is a possibility, I have a very, very complex situation, then maybe I need to use something of high order, which I call complexity. You need to use a high complexity method in some circumstances. But in many circumstances, and you know the sinusoid, if you're looking at physics, chemistry, biology, there's many oscillatory phenomena, and these oscillatory phenomena basically periodic functions. And periodic functions do not need ninth order polynomials. Try. This is the big, big danger of machine learning, is that it's very easy to do too much. You do too well. You do such a good job that in fact you're doing very badly when you test. Because the test data, by definition, was not used in the training. The test data is a point here, or it's a point over here. The test data is xi's, new xi's that were not used in the training. So you have to make it. So this brings us to the point of validation. How do we prevent this? You can measure it. What gives us 2 points. When you measure the performance, you can get very, very good performance for a very, very bad model. This is a terrible model. It's a catastrophic model. But your performance is fantastic. Mean square error is considered to be one of the best ways of measuring. Be careful. This is reality. It's not because you have a small error. In numerical analysis, small error means good performance, good model. Yeah, a small error can mean very, very bad model. And you can also have a bad model. You have a bad model with a good performance. You can also have a good model with bad performance. Just to tell you, because I don't have time to go through these things. I have many examples that show that you can have a very good model which has bad performance. For various reasons, we won't get to that now. Just to show you that things are not very simple. One has to be very, very careful with machine learning. Because I'm a mathematician, so I know what it means to have a good method, good convergence, good precision, good accuracy. And so I'm not going to fall into the trap of machine learning which says, oh, yeah, go to GitHub, take the code, it takes like, just run the thing until you get a small error and then you're finished. What happens is you're going to fall into this trap. You will fall into it. Okay, so how do we avoid it? How do we prevent this? We do validation. So validation becomes very, very important for any machine learning. Listen, What I show you now, I showed you an example because it's easy to visualize, but in fact it's a principle, it's a basic principle of all machine learning, and you can prove this mathematically. You saw what's happening. This is the order on the axis, on the x-axis. I'm increasing the complexity of my model. If it's a polynomial or regression, it means it's the order of the polynomial. The green curve is what's called the training error. It can be shown mathematically the training error will always increase as you increase the complexity. Why? Because you're getting closer and closer to the noise. You're getting closer and closer to every point. You saw. You're pushing the method, you're pushing and pushing and pushing until it manages to capture all the noise in your training data. But what we really use is testing the method. So you can show mathematically that as the order increases, your test error, so this is the training error, and this is the test error. Sorry, on the y-axis, it's the error, prediction error. Okay? Of course, we're interested in how well our model is going to predict. That's why we did machine learning. That's why we model it. We want to be able to predict. We don't want to reproduce what we know already. The points we have, we know that. No reason to want to go beyond these points to see what would happen if something else changed. And so we can show mathematically, here's the explanation. As this one decreases, this one will increase. So if you take the sum of the two, you get this U-shaped curve. A U-shaped curve is a curve of model confidence, or what's called the curve that describes the bias variance compromise. So what's happening mathematically is that your bias is getting smaller here as you increase the order of your method. And what's happening as you increase the order of your method, your variance is getting higher. So I hope you know what bias and variance is. Bias is the difference between the mean values. It's how far bias has to do. So this is low bias. Low bias means that on average, your results are close to the center. Okay? High bias means on average, your results are far away from the center. It's like you're aiming for the center. That's the bullseye. So if you're playing darts, you play darts in Southeast Asia, you want to get, that's the target. The target is the red point. Okay? Low bias methods means on average, you're okay. High bias means on average you're far away. But the problem is, as you get lower bias, you get higher variance. Variance means that your results are more spread out. So your results are spread out, and your results are spread out. So at some point, you have to make what's called a compromise. Okay? You have to make some kind of compromise between bias and variance, which you have to say, I don't need to have an error very, very small, which means I don't need to have a bias that's very small. Why? Because I don't want my variance, the uncertainty in my result to be too high. So there's some point of compromise. The compromise is that's the minimum of this curve has a minimum. I showed you this curve. In fact, the curve is here. In reality, this curve is just an idealization of this. It's exactly, you see the shape? This is real. It's a real example. Okay. It's not a nice smooth curve. You see bias going down and variance going up. Bias being training error, variance being test error. Okay, so here you go. So this curve is a universal curve, and I can show that any approximation method, any machine learning method will always have this performance. There's some exceptions on that. And you see at the bottom there's what's called irreducible error. Of course, there's some error which is there's some sigma which is the variance of the underlying. You see, in nature there's noise. Right? That noise you don't need to get rid of. You mustn't think that the noise in nature you can somehow do better than the noise. There is a lower bound here. You can never be smaller than the lower bound. The bias you can reduce, the variance you can reduce. These are these two curves. And the best, but you always have a sigma 2, which is the variance. Sigma 2 is by definition the variance of 0. You can to say it's a Gaussian distribution, as a Gaussian distribution with mean 0 and variance sigma 2, then this irreducible noise is a point below which you will never get. You cannot do better than the then they don't try. So this curve is very, very important. It's to warn, it's to help, to guide you in choosing a method. Because you're going to choose your method to obtain what you try to do. The compromise means, as I said, you choose a method with the lowest possible complexity. And you remember in my table at the beginning, and all this, and that's why I put the complexity in my table at the beginning. It's a long time ago. Remember, it was all here. Why do I put this? Now you understand why I put this column there, next to my method. Complexity. Nothing. Complexity, it becomes a very, very important factor in the choice of the method, because the complexity means you're going out of the year. You're going out on the x-axis, you're going to get x. So as you're going out, you're getting smaller and smaller. Training error, but be careful, your test error, because of the variance that's going up, your bias is going down, the bias is the first step. The variance as you go down, as your bias goes down, your variance will go up, and you're going to get some point which you have to look for, which is a compromise. That's always present. This, what I show you, is valid for any and all machine learning methods. Whatever you do, you always have this possibility to increase the order, either by using more complicated methods or the same method like linear regression. You can ask the linear regression from higher and higher order. And this is what it is. So this is very important. And must always be kept in mind when one does machine learning. So, there are no machine learning methods that simultaneously, this is a theorem, right? This is a law, this is a truth. One thing I can be sure. It does not exist a machine learning method that at the same time will have small bias and small variance. There's nothing out on the left-hand side. You cannot have at the same time a small training error and a small test error. A small training error implies, and that's mathematical. That's because of this. If you develop, you look at the MSE. Yeah, this is MSE. You look at the MSE and you expand it according to this definition. You can see that decreasing bias will increase variance, and at the same time increasing bias can increase variance. So this is mathematical, it's not just an observation. And then we must always be prepared to sacrifice some of the bias, but some accuracy, to reach a lower variance, since this is the most dangerous for what's called predictive performance. What we're interested in is not the performance in training. We're interested in the performance of our method when we use it to predict. That's called predictive performance. So it changes completely from what everybody's been teaching you in classical numerical analysis and classical computational science. We must not look for small error. We have to look for error that's reasonably small to ensure that we do not go into the regime until the part where we start to get increased variance. And as I said, this is valid for any and every machine learning method. So there are what are known as low bias machine learning methods. These are the ones that can be chosen if what's important is to have low bias. These are decision trees, KNN, which is K nearest neighbors, and SVM, which is support vector machines. These are machines, you find them in my table, okay? Just go back, and then to see what is SVM, what is KNN, then you have to go to the books, to the internet, to my courses. Afterwards, for me, it's just technical details, but not really important. What's important is how to choose. Once you've chosen, then the answer matches. And they're also what are known as low variance methods. So linear regression is known to be a low variance method. This is what's called linear discriminant analysis and logistic regression. Okay, these are different methods. We don't have time to say to go over. It's very useful to have some kind of classification, to know, to have some initial indication of how to choose a method to solve. And now we come to performance scores. So always when you publish or when you give your whoever you prepare your statements, machine learning. I made a zoo, there's a zoo here. There are many ways to measure the performance. Okay? This is one of the ones. There are Regression itself, it's, as I said, it's the only machine learning method that gives full diagnosis, because regression has a lot of hypotheses, assumptions, and so because that regression, it's called linear regression, sometimes it's called simple linear regression. It has many hypotheses on the distribution of the noise and the independence of the noise, and it enables you to have pretty exhaustive diagnostics. I like regression because you can have full diagnostics on the performance and the predictive performance of your model. Classically, in statistical analysis, one uses p-values. P-values has what's called significance levels. We would say that my method has a significance level, significant to a level alpha equals 0.05, and you have what's called p-values. P-values, which were used until the year 2000, basically considered as the best way for measuring performance. Today, one does not use them anymore. It's been shown that p-values are not useful in real situations. They can lead to and they have led in the past, to very, very catastrophic decisions, especially in terms of clinical trials and medicines, drugs that are put on the market, because the main criterion for succeeding if the pharmaceutical wants to make some new treatment, the treatment has to undergo statistical tests and statistical trials, and one usually was reporting the p-value. It was considered to be the gold standard. If you have a p-value less than 0.01, 1%, or less than 0.1%, these were considered as being very, very good models. And it has been discovered that one should not use them anymore. So this is like since 2014, I think like 10 years ago, the big Statistical Association of the American Statistical Association, ASA, made a public declaration that we should no longer use p-values. Anyway, just to show. And then, for those who know, everybody who does statistics in school or in first year university or second university, they always teach you p-values. Today, I don't teach p-values to anybody anymore. They're very dangerous p-values. I just warn you about. These are things that are not written in books. It's experience. And then what one usually uses is MSE and MAE. That's mean squared error. That's mean absolute error. Instead of taking the square here, I can take the absolute error. There's different reasons to take absolute and squares. There's a lot of, you have to think a lot about your performance measure. It's not as simple, as I said, as in classical numerical analysis. What's used a lot is what's called R2. R squared, in any machine learning method, most machine learning methods, if you use the code, it's scikit-learn or PyTorch or TensorFlow, they will always report the R squared value. R squared is also a performance measure that has to be used with caution. There are cases I told you, say here, and a bad model that have a good score, and a good model that have a bad score. For all of these instances, you can be confronted with this apparent paradox that I'm showing you. I don't have time, I need to come back and spend a few months to show you all these things. Okay? But this is a warning, right? Do not blindly accept the fact that somebody has a small error. And once you're falling into this, just remember, if you remember one thing, remember this, and remember this. Small error. Very small error, okay? Your performance measure, MSE, small errors. Great. I've got the best model. You can have a very bad model with a very good score. Be careful. You're going to fall. Everybody falls into this trap. So what can you do to prevent that? Well, be careful. I think it's easy for me to say be careful. What can you do? You see, I have one line here in yellow, predicted versus observed. In the end, the only way you can really know whether the score that you got gives you a reasonably good model. If you've got a good score, or you've got a reasonable score, you want to know, do you have a good model or a bad model? So what I like, I always ask result is to plot predicted versus observed. So what does that mean? Very simple thing. You project onto predicted value, measure. Real. Not real in terms of real investment. Real. So now, if the world was perfect and there was no noise, what would happen? You know what would happen, huh? What would I get here? I would plot predicted and in fact everything would fall onto the line y equals x. That's a perfect model. If somebody shows you a result of a perfect model, immediately say, I don't believe you, but that doesn't happen. That cannot happen. That's impossible to have a perfect model. So it means, in fact, there's no noise, and everything is perfectly predictable, and life is boring. So what's going to happen, in fact, is you're going to get what's called a scatter plot of, for this predicted, for this observed value, which was here, I got this prediction to get a partiality. You're going to get a cloud plot. It might be more or less. These are points, and that gives you a scatter plot or a cloud of points, which enables you to some extent to evaluate without looking at the value of the MSE or the MAE or the R squared, which can be good or bad. This gives you a much better visual proof which a human being can evaluate and say, that's a good compromise. Okay, I might have some scatter here if you like. The MSE might be big because my points are not close to the line. A very small MSE would have points like this. If I had a small MSE or a small R2, my points would be very close. And that's small. The black one has a rather big error, but you see, what's good about the black points, which is Mod 1 model, is that you're capturing very well the underlying. For big values of observed, I'm getting big values of predicted. For small values of observed, I'm getting small values of predicted. It's true that there's some noise, there's some error around, but this can be, the black can be, for example, can be a good model with a bad score. Doesn't mean that you have to throw it away. It can still be good. And sometimes what you see is if you have a bad model will be something that the points will be out. That's completely, the observed values are always much bigger than the predicted. Or you can get a model that has points out. Okay. Then you see that your observed values are always much smaller than your predicted values. So visually, you can see if I get a result like this, when I plot, okay, this is just a plot of y, that, y. That's all I'm plotting. I'm just plotting y hat, y is a vector of n points, y is a vector of n points. These are these guys. Y hat. Predicted values, y. So just very simple, huh? Very basic thing. Okay, for me, in the end, otherwise, we have to be very suspicious. Because we scientists, as I say, it's not a matter of choosing a red shirt or a green shirt. So it's not serious if there's an error, my prediction method doesn't work well. Yeah. Be very careful. And this will happen on it's with nothing to do with the fact that it's a linear regression. This is true for any, and this is my advice. People don't like to do it, this scatter plot, because it shows that, it really shows what your method is doing, right? You can hide it. With a score, you can hide, the score hides a lot of details. Good score, but remember the 9-field polynomial, terrible model, excellent score. And this will happen. This happens all the time, especially with neural networks, which are known to give very, very good scores, but to have very, very high variance or very high test, they can have very high test error. So it has to be checked very, very carefully also. So to check these things, one does systematically what's called model validation to avoid this error, the static problem. This is checking once I finish the. So how do we go about it? Systematically, it's been decided because we are dealing with, this is one of the very, very good things that has come out of machine learning. Machine learning people, when they develop these models, these methods, they realize that one of the major problems that I told you is that when you take your population, okay, the model, you take your data, the data is a long, let's say it's a long block like that, many points and stuff. And the question is, if you develop a method on this half of the data and you develop a method on this half, you take half the data and the other half, you want to be sure that the difference, because we have two different models, you're going to be sure that the score, the performance you predict, takes into account the diversity in your data. The data will always have diversity, and you have to somehow take that into account. So the most honest way to do that is to divide your data into what's called a training set, validation set, and a test set. So this is a way. You remember the two curves, the training curve, the points go down, the test curve, the points go up. Usually what one does is one takes even more proportion. So don't worry, machine learning people in Google, they're not stupid. Right? They don't think. But they realize that what they promise is sometimes not realized. That's it. Bad models will have good scores, good models will have bad scores. So how do you give tools that can be used by everybody? You insist or you require that models should be validated. This validation has various forms. I don't have time to go into all the different ways of validating models. But basically, you see what happened. I trained at degree 1 and I got an error of 7.3. This is the mean squared error. Okay, but just for this is exactly the result that I took from the linear regression, the regressions that I did at the beginning. I won't go back. Training at degree 3, you see, I get a small error, but I'm training with degree 10, I don't know why I said it's 10, I'm trying 10.5. Anyway, for each of these models, I can get a test error and a test error. Here, it should be small, I don't know what's 10. It should be small, I don't know, there's some problem, I should check. Anyway. In the end, once I've trained, I should make some compromise, not to take. This is maybe the problem. In this case, I don't remember this is big. In this case, you can see the error on the validation set that was the smallest was 1.1, and I'll use this model as the best choice to get a test error. But this is not completely. This is one way. This is a good way of choosing what is the good complexity of the model, and then in general, it's used to get some idea of the distribution of the errors. So, in general, that's not enough. One has to use what's called k-fold cross-validation. So, I mention this because it's used systematically, and most of the machine learning algorithms and the codes that you find in R, that you find in scikit-learn, that you find in Python, they provide the possibility to do cross-validation. So cross-validation is a bit more sophisticated. It says, I check the training data, I divide the training data into, let's say, five pieces, they call folds. You fold the data 5 times, and then what you do is you train on these 4 and you test on this one. Then you train on these 4 and you test on this one. You see what you do. This way, what I'm doing is somehow mixing the data so that the model that I train doesn't have, it could turn out that the data you collected, some of the data is very good, and other data has more noise. And some data will be less noisy, some data will be more noisy. There can be diversity in the data, and you want to be sure that your model does not, by luck, to could be lucky, you could be lucky. You choose data that gives you a certain model with a very good accuracy. It could be this one. But by one, taking each time 20% of the data and creating a model, you find some parameters, and those parameters are usually the average parameter, and not the best one. Because the most honest model you can find is not the best model of all of these, but the average model. Why? Because at least, why are we doing all this? Because you're going to test your data. Your training can give you a false impression of having done a good job. As I said, your training is dangerous because your training is not representative, and because we don't have infinite amount of data, what we do is we take the data and we pretend that 20% of the data in this case is not used for training. Train on this, test on that. Train on all these, there are 4, test on this one, train on this 4, test. So you see, we exploiting the data we have in the best way possible to be able to be sure that when it's used for testing, you give it to somebody, okay? When you publish, and somebody comes to take your method, you have more or less, as best as possible, covered all the possible cases for testing. And then what you do is you also keep some data completely aside. I could put this in this color also. It's just to show that inside the validation, it's called the validation stage. Inside the validation stage, one fold, or usually is 20%. If you're using this called K fold, means K equals 5 in this case. I divided my data into 5 equal chunks. These are chunks. And I still could keep some test data completely away from the training. You understand why now? Because you can get it. You want to test your model, your final model, on data that was not used to train it. It's tough to test your model on data that you used to train. Of course, the training data, that's your job. Your job is to use the training data to get a good accuracy. But that does not mean that the accuracy will be the same as the test data. So, there is, all these things are built in. They're pretty easy to use. In scikit-learn, if you use scikit-learn, most people use scikit-learn in machine learning and PyTorch and TensorFlow, etc. These things are very easy to use. You just say, I want K-fold cross-validation with K equals 5. Then, very easy to use, but you need to I always say we are mathematicians, we want to understand how things work. Why do you need to understand how things work? Because you need to be responsible for the results that you do. So this is one way of ensuring, as far as possible, the performance, the predictive performance of your models. This is very, very important. So usually there's a big question that you have to choose K. That's not an easy choice. Okay? And can have influence on the parameters. So usually what we say K must be representative. Okay, that's very easy to say. It doesn't help you. But usually one use, if it's possible, if you have large data sets, you use K equals 10. But it's known to give a small bias and modest variance. If you don't have enough data, you're going to chop your data into K pieces. If in each piece there's only two data points, it's not going to be very representative. You need sufficient data in each chunk, in each division, so that data is representative of all the data. Okay? So this is why if you have big data, it's great. When you use K equals 10, very often it turns out we don't have such big data. So in that case, you use K equals 5, and you can use K equals 2 if n is very, very big. It's sometimes very big because. Why do I say we're very large n? Because in some data you've got millions and millions of points and it's too long, it costs too much to do all this repetition so many times. And if you have small samples in general, you use what's called repeated trade tests. In other words, you take this whole thing, you take this setup, K equals 5, and you repeat it 5 times. You don't, when you do repetitions, you don't choose exactly the same data, but you know when you play the card to shuffle, you redistribute in a random way your data, and then you choose folds, and these folds are not the same as before, because in between every repetition, you reshuffle, because you re-choose or you reorder in a random fashion for your data. So by doing random reordering, you can take as much, you can exploit your data many times. Okay, so anyway, just to say, this is a big thing because it's necessary because to take precautions so that you can be sure as far as possible of the predictive performance of the model. Okay? Because as I said, you can train it well. No problem. Everybody can train. Because now we have these fantastic software tools. And you just take it. And you want to have a neural network of 100 nodes, 100 neurons, and 200 layers, or you want to have 1 million neurons and 3 million. You just put the numbers in, and the machine, if you have a strong enough machine, it's very, very easy to use these things. So that's why one does this systematically. And then what we have spoken about what's called hyperparameters. Okay, so when a machine learning method learns the model has parameters. The parameters are usually coefficients. In the case of linear regression, the parameters of a linear regression model are the coefficients of the linear regression equation. You know, linear regression, it's y hat equals beta 0 plus beta 1. This is linear. Suppose that I have x1 and x2, I have temperature and pressure, okay? And I want to get the approximation of the concentration. So, the vector beta these are the parameters of its vector. Like this. So you could sometimes consider the line vector, sometimes a column vector. Usually it's a line vector. And there's nice ways of expressing linear regression in terms of matrix algebra. It's linear algebra, that's not linear algebra. So these are the parameters of the model. So what are hyperparameters? Hyperparameters are parameters of the method, not of the model. A hyperparameter in this case, in terms of linear regression, would be the order. These x's in principle can have exponents. It can be x1 squared, x2 cubed, etc. So they are what we call hyperparameters, which have nothing to do with the parameters of the model, but are the parameters of the method. So, as I said, it sounds very easy, but in fact there's a lot of very fine and very delicate points that have to be taken into account when using machine learning. Machine learning, we would like this to be magic, but it's not magical. You have to work hard to do machine learning. It seems like it's going to solve all the problems in a magic way. And it can, but it needs to be cross-validated, it needs to be tuned, and it needs to be hyper-tuned. So hyper-tuning is due to the fact that all machine learning methods have what are called hyperparameters. And they almost always need to be tuned. Okay, when I say almost always, because when you use support vector machine or random forest or logistic regression or all these hyperparameters of the method have default values, so they are default values. Okay? But be careful, the default values, they only work when they work. Okay? And you have no guarantee that they always work. They only work when everything's okay. But usually everything is fine. So these hyperparameters always have to be looked at, and usually what one does is one does what's called an exhaustive grid search. So you give intervals of values for the hyperparameters. Say a method has 3 hyperparameters, so you give 10 values for hyperparameter 1, 10 values for hyperparameter 2, and you have 10 by 10 by 10, you have 1,000 models to compare. And then what you do is you do some kind of cross-validation. I won't go into it in fine details. You try every single one in the cross-validation, you try every single one of them. Every combination, every possible combination of the 3 parameters, if there's 3 hyperparameters, and then you decide out of all of them which gives you the best performance. Okay? So there's always a model predict. You always have result of them. There is some cross-validation which is used here as well to be sure that while you are doing your hyperparameter tuning, it's also being tested on different segments of your data to be sure that it's not working because some of your data was training and some was test. But what happens if you switch and you put other data to test training? Okay, these are not simple things, okay? For me, the machine learning itself is simple. This is what's difficult. But this is what takes all the time. To say I'm going to use SVM and you call the SVM routine, anybody can do that. But this requires work. You have to sit, you have to be careful, you have to be systematic. And if you don't do this, I promise you, except if a miracle happens, things will not go well. Because you saw the problems. I showed on my stupid example of the regression of the sinusoid function. You see, so many problems can arise, and they do arise. That's on one simple example I showed you. Imagine what happens in complicated example. Okay, so Google, Microsoft, they spend a lot of time and money doing hyperparameter tuning. It's one of the major challenges. So people are interested. There's very nice work on it's called Bayesian optimization, which can be used to solve the problem. So, alright, so now I finished with machine learning, okay? Sorry, very quickly. I tried to show you things that are meta, global, universal things that are applied to all machine learning. Every machine learning method you're going to use, you're going to, as a serious scientist, you're going to have to go through all this stuff that I spoke about today. Okay? Believe me, 95% of the time will be spent doing this stuff, not choosing the method. So, okay, I want to see about use cases. So, just to show you, just to show you that all the methods that I mentioned before are indeed used in many applications, many use cases that I've chosen. I found a lot of use cases in health and medical sciences. That's the theme of it. You could say machine learning has nothing to do with health and machine. That's true. With machine learning, you can apply to anything. We're interested in applications for health and medical sciences. So, SVMs and random forest is one of the spoke about decision trees. Random forest is a very good way of using a decision tree. It's an aggregation of decision trees. It's used a lot for medical imaging, such as X-rays, MRIs, to identify patterns associated with specific diseases. Now, that's going to do diagnostic. Very complicated MRIs and X-rays, they can do diagnostics very well using rather simple SVM, not even neural networks. For example, I could train an SVM on a data set of many mammograms, which are labeled as normal cancers, and you can create a computer-aided detection system for breast cancer. I showed you yesterday, the NLM seems to do much better, but you can use what I like about SVMs or random forest. These are methods of relatively low complexity, so you can have, as a scientist, you can have much more confidence in their predictive performance. Okay? And then, these are special type of neural networks. It's called convolutional neural networks. It's a special type of neural network. They have very good pattern recognition capabilities. They're also often used for pattern action and disease diagnosis based on imaging. Okay? There's a very lot of work on drug discovery. Okay, that's been done by big pharmaceutical companies. So you can use machine learning, okay, what are called graph convolutional networks, to learn structural features of molecules and predict their biological activity. The one thing you need to know with the drug, when you're developing a new drug or choosing the components of a new drug, you want to know what its biological activity is going to be. So there's a lot of machine learning being done, clustering, classification, and regression. And yeah, I have some list of some of the methods that are used and some of the applications. Molecular design, feature selection for biomarkers, single cell data, etc. Target disease drug associations. I found a very nice collection here of the different types of use cases that are associated with drug discovery and the machine learning methods that correspond. So you see machine learning is used, it's being used, it's still going to be used all over the place. And you find, random forests here, you find K-means, these are clustering. Remember, clustering is unsupervised, so these are unsupervised learning methods. Classification and regression are supervised learning methods. And so you find a collection of running forest instead. These are all the methods that I mentioned before. So you can see that which one to use in which case, after that you have to go to look at the literature. What very often people do, researchers do, if you're the first person in the world and you cannot find anything on a Google Scholar or something that tells you, well, for this type of medical analysis, what should you use if you want to train a machine learning model, what should you use this type of machine learning model. You cannot find anything. What people do is systematically, it's easy because even a laptop can do this stuff. So you try 4 or 5 or 6 different methods and you compare their performance. And then from the performance comparison, you choose which for your data turns out to be the best method. I cannot say to you, well, you should use SCM for medical imaging data. It's not true. I don't really know because your medical imaging data have never been studied before using machine learning. And so the best thing that you can do is to try SCM, to try random forest, to try regression, multiple regression, and then to try a neural network. And then, as I said, look at the predictive performance. In particular, if you can, make some kind of predictive observed plots. You have to do these one by one. I won't get to the details. Basically, something like that. And then, as I said to you before, always the same rules apply. Choose the method of the lowest complexity or the lowest order that gives you acceptable performance. It's always a compromise, and you're not going to get. Don't go look for the most sophisticated method, which people think, the more complicated my neural network, the better it's going to be. Be careful of overfitting. It's going to happen. So, just to show there's a lot of methods here, which one do you choose? I don't know. If you don't know either, you try 4 or 5 methods, and as I said, choose the method of the lowest complexity. That's why we have the table. It gives you reasonable. And then today, the hot subject is personalized medicine, what we call digital twins. So now there's a lot of. The idea is that the digital model is going to be some kind of replica, it's going to imitate what's happening with the real. So this is the real person, and this is the digital replica. So this digital replica, it uses all your medical data. It takes it in, okay? And you can test treatments or test diagnosis on the numerical model, and then apply them to the human, and then the measurements go back. You get new measurements, new tests, new X-rays, and they go back in the digital model. The digital model learns something else, and this is what's called a digital twin. So this is also one of the things that's been doing. A lot of machine learning algorithms can be used to analyze, for example, genetic data and health information to develop what's called personalized treatment plans. Okay, this is individual, but it could be a population, it could be a region, it could be old people, young people, it could be poor people, rich people, it could be Chinese, it could be China, it could be Thailand. It's not necessarily a single person. One can make a digital twin of a population or subpopulation which registered in public health, for example. So there's very, very interesting research being done on using machine learning to do this. And then there's many possibilities of using different machine learning methods for hospital planning, for example, admissions and readmissions. I gave a list of some applications, yes, some nice pictures which show how it's being used. So we're using what's called LSTM, is a special type of machine learning algorithm based on a neural network that's used for what we call time series. When you have events that occur over time, number of patients arriving, number of patients leaving the hospital, one can learn a model. Why do you want to learn a model? They want to predict, right? Suddenly I have an epidemic, 1,000 people are going to arrive. What's going to happen to will my system be able to deal with that, or what kind of resources I need? A good machine learning model that's learned, been trained on previous data, can be used to make analysis beyond. Always looking to analyze. You can always go back to my simple example of, of the science slide to see why we need. Okay, so that's basic machine learning. So wait, I stopped it. 10, 10. Very quickly, because this afternoon I'm going to speak about scientific machine learning. So before we speak about scientific machine learning, I just wanted to speak very quickly, because we don't know, as usual. There's more information than time. Information is always bigger than larger, greater than equal to So I want to speak very quickly about, I said at the beginning that there's huge interest now in omic data. And I did a little bit of research on machine learning for omics and multi-omics data. And I'll just very quickly show you the different type of omics data. And you go back to the slides, and each slide I'll take one type of omics data, and I've found many applications and machine learning algorithms that are used for it. And then this afternoon we'll speak about scientific machine learning. The idea now is to say, okay, machine learning is great. It learns from the data, exclusively from the data, but can I somehow use science, or use equations, formulas, scientific experience, scientific knowledge, in order to validate or to improve the predictive capacity of my machine learning models? That's the start. So, omics is it's incredible. So, omics data has become available because we have instruments. So we have machines now that generate omics data. So it encompasses all types of biological data and has a very strong link to system biology. Because we want to understand how an organism functions. An organism can be from a virus to a human to a population. We can use omics data. That's to do with system biology. And it includes, I said, genomics, transcriptomics, proteomics, metabomics. And we can use it to study biological processes. And these processes are the processes that underlie health and disease. And if we understand what we can reproduce them, we can use them to develop new diagnostics and new therapeutics. So you understand it's a very, very big and a very important domain. Evolving extremely rapidly, because the technologies for generating omics data are being developed all the time. So we have ever increasing amounts of omics data. So yeah, I have the type of omics data. There's some pictures you can see, which shows you the different types of omics data that exist. And as I say, it's increasing all the time. A very large number of possible applications. So you can have omics studies for human disease, for agriculture, for plant science, for microbiology. The list is very, very long, the number of applications that can be addressed using omics data. But it creates big challenges in complexity and a lot of it. There's a nice image which shows how we're going from DNA to molecular to microorganisms to whatever. Understanding things. Omics data is really a way of being able to address problems in diseases, epidemics, agriculture, biology, microbiology, etc. So you see it goes very, very far to understanding that. So what about data science and machine learning? Okay, so as usual, there's the whole knowledge discovery process. You have to acquire curation to stop to archive the data. You fuse. You have to use certain principles which should be respected for the integrity of your data, the privacy, the respect of privacy, the availability, etc. And there's many regulatory, ethical, legal, social issues. So this is data that's been lacked. So you have to be very, very careful about how it's done. So this is a basic diagram which shows the overall workflow of how you get data in, what you do with it, and how you can process it to produce some results. This is very general. So Machine learning for omics, in fact, all the stuff that I've shown you very, very quickly can be used for omics. Now, unsupervised learning, supervised learning, reinforcement learning, in unsupervised, in supervised regression classification. So here I have an example, disease classification. And then you know, anyway, single cell classification, gene expression, cell phenotype. But this is just to show you to what extent machine learning in all its different variants has been used and is being used for analyzing omics data. So, for example, supervised, unsupervised. The list is very, very long. I took this, so there's some nice review papers available. I put the review papers, all the stuff, in fact, I took, also I extracted that from some very nice papers, which this came out in 2022. There are very recent papers which give nice reviews of all the different uses and many, many references if you're interested in going into the references of the use of omics data. A lot of work on machine learning for genomics. Okay. Here you have a diagram which shows all the different, which brings together all the different possibilities of using machine learning for genomic data. I'm not an expert, at least I give you information if you need to go further. For transcriptomics, how the genes are transcribed going through the RNA, okay? And then operational neural networks, GRUs, these are neural networks, just a time series, residual network, etc. So you see there are many, many, many uses of machine learning for transcriptomics. For proteomics, you just do the study of the proteins. Okay, there's also a lot of work being done on proteomic data using machine learning, different types of machine learning. It's very, very big over what's being done. And for the metabolomics, it's just analyzing all the metabolites in an organism. Okay. The relationship that they have with physiological and pathological changes, so you can understand that the proteins participate in the metabolism, and the metabolism has a direct effect on physiological and pathological changes. And then you find all the threads, SVM, naive phase, random forest discriminants. I've mentioned all of these in my tables. And then radiomics, well, today radiology is called radiomics, it's just an analysis of imaging data. So, of course, imaging data is being analyzed more and more every day using machine learning. So there's many, many applications of that. And now we get all the way down to single cell omics. So the idea is if you can understand what's happening at a single cell level, then you can understand what's happening at an organ and then an organism. Okay, so you can go very, very far with single cell. There's a lot of work now looking at genomics, transcriptomics, proteomics, and then proteomics of a single cell. Hoping that afterwards we have to reject to high levels. And then the latest thing is called multi-omics. You put genomics and proteomics and transcriptomics and etc. and you try to put them all together and to have, for example, precision medicine. Gives you much more precise views. Okay, so this afternoon we'll speak about scientific machine learning, which is now something that is very important for us. How do we take all the PDEs, all the ODEs, all the conservation laws, all the effects of symmetry, conservation of mass, conservation of energy, etc. Can we use those in order to ensure or in order to force the machine learning model to be at the same time a model that minimizes this? Okay, that's okay. That's what's called data-driven. This is only data. There's no theory there at all. There's no mathematics. There's no diffusion equation. There's no SIR. There's no Navier-Stokes. There's nothing in there. But we've been, scientists have been working for hundreds of years developing all these fantastic mathematical models. The question is, can we use these mathematical models together with what's called model-based science, together with data-driven science? This is driven by the data, but we also want to base it on the model. Can we put them together? And it turns out that yes, we can. And there are many, many ways of doing it. But that was just see, I need to come back in for another 100 hours, and we can speak about all of it. So in an hour and a half, I'll show you one possible way of doing it. And I'll mention all that. Okay, so have a good break. And I'll see you. Now,